Hello students, welcome to the 20th lecture on particle physics, and we were discussing about solar neutrinos in the last lecture. And what I had told you, that protons are burning inside the core of the sun, and per second 10 power 38 protons get consumed. Since there are 10 power 57 protons, the mass of the sun is 10 power 30 kilograms. Therefore, if you use Avogadro number, then you will find that 10 power 57 protons are there inside the sun, and therefore it will take about 9 billion years for the protons to get consumed in the nuclear fusion process. Now, when this nuclear fusion process starts in the stars like sun, we say that the star has come on the main sequence. Therefore, here I am showing you the curve which is known in the literature by Hertzsprung-Russell diagram. The left hand side on the y-axis is the absolute magnitude, and the x-axis is the temperature of the surface of a star. Recall that I had told you the surface temperature of our sun is 6000 degree Kelvin. The surface temperature means I am talking about the average temperature of the photosphere, the surface which we see every day. Similarly, there is surface for every other stars, and there we know that trillions of stars in the universe, and they are not all of the same type. In fact, in the literature, we divide it into 7 broad classes on the known as the spectral class. They are O, B, A, F, G, K, M. And then there is 2 more, R and N. Therefore, O, B, A, F, G, K, M, R, N. And this O, the temperature is almost 50,000 degree Kelvin. KB, this is around 25,000 degree Kelvin. This is around 12,000 degree Kelvin. And then we have G, which is around 6,000 to 6,500 degree Kelvin. Now you see that our sun lies here. That means its temperature is 6,000 degree Kelvin. Our sun is not a very smart star. It's not very luminous. There are millions and millions of stars which are much luminous than sun. As you can see that some of them have got surface temperature of 50,000 degree Kelvin or 25,000 degree Kelvin or 12,000 degree. This is average temperature. Then there is a sub classification between O and B, F and G, or all of them, 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, our sun is better known as G2 type of star. Therefore, there is another sub classification between this broad classification of O, B, A, G, F, M, K, R, N, that known as M1 type star or M9 type star, G2 star, G8 type star, and this is further broad classification. But what we see that there are trillions of stars in the universe, and all of them have not got the same luminosity. Some of really very dull stars. Our sun is also a dull star, but these have got a surface temperature of around 3,500 degree Kelvin or 3,000 degree Kelvin. They are dull stars. And then what happens? Once proton fusion reaction will stop, then depending upon the mass of the star, we can have fusion of helium nucleus, we can have fusion of carbon nucleus, we can have fusion of oxygen nucleus. Unfortunately, for stars like our sun, when proton fusion will stop, we will have the core of the star will further squeeze. As we have seen that to overcome Coulomb barrier, the temperature of the core should be higher for the alpha particle fusion, which cannot happen with 10 power 7 degree Kelvin, cores of the star start contracting. Then a time comes when these temperatures are enough for the alpha particle fusion. Now, when the core is contracting, the energy is getting released, and the outer envelope of the star is getting expanded, and the star will become a red giant. Therefore, our sun, after this main sequence, which is shown by this broad line here, this line, diagonal line that has been shown where our sun is lying, this broad line, from here the star will become a red giant, or for massive star it will become a supergiant, and then depending upon the core mass of the core of the star, it can become a black dwarf or white dwarf or neutron star or black hole. That we will talk about. For example, our sun will become a white dwarf star. After red giant, there will be no fresh fuel to have alpha bonding, and therefore gradually the energy or the luminosity will start decreasing, and finally it will become die as a white dwarf star. Now, there is no need to go into the detail about it, but we will come back to this. Therefore, what we are talking about, that inside the core of the sun, nuclear fusion reaction is going on, where proton-proton burning is taking place. And what I have told you, that since photons are really getting produced, but because of electromagnetic interaction, they have multiple of scattering, and therefore it takes almost 200,000 years for a photon to come out. And therefore, the light which we are seeing today are not those photons which have been immediately produced by the sun, but they are more than 200,000 years old, which we are seeing today. While in the case of neutrinos, since neutrinos interact weakly, therefore they come out and they travel with the speed of light, that means 3 into 10 power 8 meter per second. Then we also know that the Earth-Sun distance is about, from the surface of the sun to the Earth, it takes 8 minutes. So therefore, 8 minutes means 8 into 60 seconds, that is 480 seconds. And light travels with a speed of 3 into 10 power 8. Therefore, the distance that it covers, which we know by the name 1 astronomical unit, this turns out to be of the order of 10 to the power 11 meters. Therefore, this 10 to the power 11 meters, 1 astronomical unit, it covers in about few seconds. Therefore, this is how the neutrinos come out per second, and as I have told you, this is around 10 power 11 meters. Luminosity of the sun is 10 power 38 nuclear reactions per second. Therefore, it is something like you have a tennis ball and you cover it by a football. Therefore, this is the tennis ball where where your sun is, and then these neutrinos are getting emitted all around, and they will spread all around. And that means if you have covered it by a football, here I am showing it by this green line. Therefore, in equal numbers, from the sun, it will go out in all the directions. Suppose on this football, which has got a radius of 1 astronomical unit, we are somewhere. Okay. Therefore, we are at a distance of 1 astronomical unit, and we have covered this sun, which is a sphere, by another sphere, which I am calling it as football, and then the radius of that football is 1 astronomical unit. Now, the luminosity of the sun, we have seen that 10 power 38 nuclear reactions per second are taking place, and then that means you multiply it by 2, because for each 4 proton burning, there are 2 neutrinos. Therefore, in general, there are 2 into 10 to the power 38 neutrinos they are getting produced per second. Now, among these 2 into 10 to the power 38 neutrinos, they will spread all around. How many of them will be able to reach per meter square per second? That means you divide it by 4 pi r square, and r is again one astronomical unit, and that is 10 power 11 in meters. You are converting it into centimeters, and then 4 pi r square is 10 power 27 centimeter square. You divide it, what it will turn out in centimeters, that around 10 power 10 neutrinos per centimeter square per second, they are coming from the sun. And the most important point is that they are not only coming from the sun when it is on our head, or where we say that in India we have day. No, in the nights where the sun rises in United States, or say Canada or somewhere else, then also neutrinos are getting produced in equal numbers, and they are traveling, except for the fact that now they have to travel the Earth also. Say the radius of Earth is around 6400 kilometers. Therefore, this is the extra distance that they will travel. But again, since their interactions are so small, that per centimeter square per second, you have the equal number of neutrinos which will come from that direction. Therefore, it is expected that neutrinos are coming to us all around from sun, and the numbers are 10 power 10 neutrinos per centimeter square per second. Roughly, you can say that 70 billion neutrinos are coming to us per second. That is why yesterday when I was showing this thumb, I was telling you that trillions of neutrinos are coming to us per second, crossing our thumb and our body, and we don't realize their presence. This is because they are weakly interacting. Once in 75, 80 years, one is expected to interact. Otherwise, there is no chance. Now, to detect these neutrinos, many experiments are going on since the last 70 years, and many have observed these neutrinos. And the recent major detectors, for example, it was Davis who started looking for solar neutrinos, and he performed that experiment for about 25 years. And then we have the major experiments like Kamiokande, which had started in the 90s, 88, 90s. And then we have Sudbury Neutrino Observatory in Canada, Borixino, Geno, Super K. Super K is the revised version of Kamiokande, bigger detector, clean experiment, lens experiment. There are many, many experiments which are going on to detect these solar neutrinos. And the other important point is that when we talk about proton-proton chain reaction, this is not a single step reaction. I have told about helium-helium nuclei. They are burning to give you helium and proton. Besides that, 2 positrons and 2 neutrinos come out. There are other pp2 and pp3 chain reactions where you can have, these are known as neutrinos coming from such channels are known as 8 boron neutrinos or beryllium neutrinos or etc. Therefore, you have boron neutrinos, you have beryllium neutrinos, you have other processes which give rise to neutrinos. Therefore, in general, we broadly tell about pp chain reaction, but pp chain reaction is further classified into 3 broad groups: pp1, pp2 and pp3, and these neutrinos we call it as boron neutrinos, beryllium neutrinos, etc. Then when we talk about heavier stars, which are massive, then there in the core, it is not the pp chain which dominates. It is the CNO cycle which dominates, and where the fusion of that gives rise to energy. And here also, as you can see, that neutrinos shown by the reds, they are getting produced. Therefore, even for the massive star or low mass star, neutrinos are getting produced, and neutrinos are coming from all other directions. Therefore, we have broadly pp chain as well as CNO cycle. Like in the pp chain, we have pp1, pp2, pp3. Here we have CNO1, CNO2, and they are the sources of neutrinos. Now, what I am telling you, that these neutrinos which are coming from the sun through pp1, different beryllium neutrinos, boron neutrinos, pep neutrinos, etc., that the reactions which I have shown, they don't have unique, all of them the same energy. For example, here you will see that pp neutrinos, notice here, pp neutrinos, which are giving rise to these neutrinos, or here pep reaction, 2 protons and 1 electron, giving rise to deuterium and neutrino. Here they are having different energies. Therefore, this is pp, this is pep. Therefore, pp neutrinos have maximum energy of around, say, 0.4 MeV. Then you have hep neutrinos, which have energy of the order of up to maximum of 18 MeV. Boron neutrinos, they have got energy which is slightly less than that. And therefore, the detectors that we talk about, they can be sensitive to boron neutrinos, or if they are sensitive to, say, beryllium neutrinos, then they will also be sensitive to higher energy neutrinos. Therefore, in the experiments, it depends whether your detector threshold is 10 MeV or 3 MeV or 1 MeV. Depending upon that, you will be able to observe the neutrinos. Therefore, the important point is that all these neutrinos, they don't have unique energy. There is a broad spectrum that will depend upon from what cycle they are getting produced. What this is pp1, pp2, pp3, or boron neutrino, they are boron neutrinos, or beryllium neutrinos, or pp neutrinos, or pep neutrinos. Now, as I have told you, that this effort of looking for the solar neutrinos, they are going on since last more than 70 years. And one fellow who has dedicated his life is Ray Davis, who almost spent 25 years of his life to observe these neutrinos. And as you can see, that they observed 0.5 neutrinos per day, that not even one event in a day. And expected interactions theoretically from the Behkal model, standard solar model, was 1.5 event per day. And this discrepancy is known as solar neutrino puzzle. Therefore, the number of neutrinos that we expect from the sun and the neutrinos that we observe in the experiment, they do not match. We find a discrepancy in the number, smaller events in the experiments than theoretically predicted by the standard solar model. And this is known in the literature as solar neutrino puzzle. And this puzzle was there since the last almost 70 years. And this was resolved by a SNO experiment, mainly Sudbury Neutrino Observatory experiment. And for that, Nobel Prize was awarded to the director of that lab, McDonald, in 2015. This was shared by Professor Takaki Kajita of Super Kamiokande lab, whose group reported the understanding of atmospheric neutrino anomaly, which we will discuss in the next class. Therefore, we have solar neutrino puzzle, we have atmospheric neutrino anomaly, and what is basically that the basic thing is that the expected number of neutrinos theoretically they are much less in number than the predicted one from the uh, theory. Therefore, the difference between theory and experiment in sun case is known as solar neutrino puzzle, and atmospheric case from the cosmic rays, we will see that. We will discuss it in the next lecture, is known as atmospheric neutrino anomaly. And let me just tell you about the McDonald experiment at Sudbury, where they took heavy water. Heavy water is nothing but D2O, and D2 means deuterium. Deuterium is the target. Okay, and what they did, this target had the ability to detect the neutrinos of all flavors. They were able to detect nu E, nu me, and nu tau. But mind it, nu E they could observe through charge current as well as neutral current interaction, as well as through elastic scattering in neutrino electron to neutrino electron scattering. For example, you can have nu E going to nu E, that is known as neutrino electron scattering. This is 6 times more than the elastic scattering for nu mu and nu tau. And then we had nu E scattering on deuterium target, which can be both charge current as well as neutral current. While for nu mu, you can have only the neutral current scattering, or for nu tau, you can have only neutral current scattering. Because if you want to just try to understand this is an important concept which you should understand, that if I have some target which has neutrons and I have a neutrino, then if this is charge current reaction, then I must have a charged lepton in the final state. And if I want to have nu mu here and mu minus, then we know that mu minus has got a mass of 105 MeV. But we don't have solar neutrinos of 105 MeV. We have seen that it is up to around in the 20 MeVs maximum energies. Therefore, the energies are small. Therefore, in the charge current interaction, you cannot have a mu minus or a tau minus, while you can have an electron, because electron's mass is 0.5 MeV. Therefore, electron's mass is 0.5 MeV. You can produce these electrons through the charge current interaction of nu E with the target material, while this you cannot do with nu mu. Therefore, the important point what I would like to raise is that in the charge current neutrino interaction, a neutrino converts the neutron in a deuteron to a proton. The neutrino is absorbed in the reaction and electron is produced, as you can see here. Okay. Therefore, deuteron is Np, and we are talking about nu E and going to E minus P. Therefore, we have, instead of N, here we have both N and P in the deuteron. Instead of N, we have P. Therefore, this is, here we are representing it by such reaction. As you can see that we want to produce an electron whose energy is, rest mass energy is 0.5 MeV. Therefore, through nu E deuterium charge current interaction, we can produce. A charge current means a neutrino has emitted a W plus boson, the quanta of weak interaction, and gets converted into an electron, and this W plus gets absorbed by the neutron, and that neutron gets converted into a proton. This is a W plus exchange, or W minus exchange. For example, if for the completeness, just I am telling you that if you have a new E bar, and if new E bar is coming, which is in the Feynman notation shown by inverted arrow, it changes to E plus, which goes out by emitting a W minus. And this W minus can get absorbed by a proton and it can get converted into a neutron. Therefore, W minus absorption by the proton will give you a neutron in the final state. Therefore, this is known, these W plus and W minus, these are the quanta of weak interaction, and through this a nu ED plus reaction is taking place where you have two protons and electrons in the final state. Well, what will happen in the neutral current reaction? In the neutral current interaction, the mediating quanta is Z0. And Z0 means this Z0 can come out from nu E. This Z0 can come out from nu mu. This Z0 can come out from nu tau. And then this Z0 is striking this deuteron target, and disintegration is taking place, deuteron breaking is taking place, and this N and P bound inside the deuteron, this is breaking into a proton and a neutron in the final state. Therefore, you have nu plus P plus N, and this interaction is not a charged current interaction. It is not going to produce a charged lepton, and therefore it is possible for the by the solar neutrinos, and these solar neutrinos are interacting with the deuteron target to have proton and neutron in the final state. Therefore, the second one is the neutral current interaction, which is mediated by a Z0 boson, while the first reaction which I have shown is the charged current interaction, which can be mediated by a W plus boson or a W minus boson, depending upon the interaction that you are talking about. Now, what they did, they had 1000 tons of heavy water, and through Cherenkov detection, they tried to observe this charged current neutrino interaction, neutral current neutrino interaction, and the elastic neutrino electron scattering, about which I talked about. And this elastic scattering is sensitive to the electron neutrinos. Using the measurement of 3 independent reaction channels, Snow was able to disentangle the individual fluxes of neutrinos. How many nu E? How many nu mu and nu tau together? That was the beauty of this experiment. As you can see that since nu E interaction can take place only through the charge current interaction, this was their number. The common number I am putting it here, 10 power minus 8 per centimeter square per second. While for elastic scattering, this was the number. And for the neutral current, the number was 5.09. Therefore, the numbers are striking. Why they are striking? This is because if you look at the standard solar model, the prediction of the standard solar model is 5.05 into 10 power minus 8 neutrinos per centimeter square per second. That should reach at Snow. But what was observed for electron neutrinos? This was only 1.76, much smaller in number, about 35-40%. But when they talked about the neutral current interaction, together for nu E, nu mu and nu tau interacting with the deuteron target and having proton and neutron breakup, they found this number to be 5.09, which was very close to the Becquerel's prediction. And this is where it was believed that neutrinos do oscillate. What is happening when they are coming from the sun to the earth? They are transforming into from nu E to, some of them are transforming to nu mu, some of them are transforming to nu tau, and in total, when we are summing these numbers for the neutrinos coming to us from the sun in the detector, the flux of nu E plus flux of nu mu plus flux of nu tau for the neutral current interaction to happen, this number is really very close to the theoretical prediction. One is 5.09 and the prediction is 5.05. And this confirms that solar neutrino oscillation is taking place, or in general neutrino oscillation is taking place. And for this, Nobel Prize was awarded in 2015. Let us stop here, and in the next lecture we shall talk about atmospheric neutrinos. Thank you.